Financial Modeling, Topic 15, Option Valuation and Hedging, Section 6, Valuing Exotic Options Using Monte Carlo Simulation. So I'm going to go to the spreadsheet in a minute, but let me just set it up. A standard calls and puts, like we discussed throughout this entire topic, we call them plain vanilla options. In other words, there's no special terms. It's just a European or American style exercise of a call or put. However, there are a class of options that are non-standard, and they're called exotic options, and they can be tailored to a client's exposure. So here's an example of an arithmetic month-end average Asian option. It's a mouthful. But let's say that the only difference between this option is the payoff for a call is the max of 0, or the payoff of the option not using simply ST minus the strike or strike minus ST for a put, but it uses an average of the month-end spot prices for the life of the option. So if it's a 3-month option, it would use the price at the end of the first, second, and third month. It's a 1-year option, it would use the price at the end of each of the 12 months. So if this were this exotic option that depends on the path of interest rates over the entire life of the option, how I'm going to model this using at-risk simulation software is I'm going to take this option. I'm going to say that it's an at-the-money option. It's a $100 stock with a $100 strike call, 2% dividend. Interest rates are 3%. It's a 1-year option. I'll assume that the annualized volatility is 25%. I'm going to again do my Black-Scholes valuation, saying this plain vanilla call would sell for 508. However, what I'm going to do is I'm going to do a Monte Carlo valuation of this arithmetic Asian whose payoff is the max of 0, the average of the price at the end of the first, second, and third month, the average of those 3 prices minus the strike. So what I'm going to do is I'm actually going to generate 3 random numbers. This is the random Z variable for the price at the end of month 1, month 2, and month 3. The current stock price is $100. I'm then going to simulate. If the stock price starts at $100 and 1 month later, my T in my model now is 0.08, which is the time between stock price changes. Now, let's talk about that for a minute. This is a 3-month option. However, I want to simulate prices 1 month, 2 month, and 3 month. So in my simulation formula, the T is going to be 1 month because I'm going to simulate 1 month and then another month and a third month. So in other words, the stock price starts at 100. 1 month later, I'm going to simulate the price. I'll then use this price to simulate 1 month later. It goes to this price and then this one. And then I'll just have a formula, the max of 0, the average of these 3 numbers minus the strike, and take the 10,000 possible payoffs based on 10,000 possible sets of 3 prices, calculate the present value of that payoff, and take the average, and that's how I'm going to value the option. So to the spreadsheet. There is my 1 month, 1/12. There's my random Z, second random Z, third random Z. Common mistake is to only have 1 random Z for each month. That would mean that 1 shock happens identically in all 3 months. No, this is 3 independent random shocks for month 1, 2, and 3. The current stock price is $100. And then I put in my risk-neutral stock sim formula from an earlier section of this topic, in which it's 1 month later and the stock price starts at $100. This is my random stock price in month 1, at the end of month 1. End of month 2, I put in the same formula, but now I'm not looking at this price. I'm starting, my S0 is actually $99.82. And it's not using this random Z, it's using this random Z. I go down 1 more formula, I get my third random Z. Also, that stock starts out at $99.65 and then has the random shock. So now these are my simulated prices in month 1, 2, 3 based on 3 random shocks. I then calculate the max of 0, the average of these 3 numbers minus the strike, times my present value factor. I'm going to run that 10,000 times, and I get a distribution that looks like this. This is about half the time this option winds up out of the money. I'm sorry, in the money and out of the money. And it looks like it can be worth as little as 0 and as much as looks like $35. However, the average payoff, the mean, is $3.60. So the price, the fair price using this this Monte Carlo model, assuming random walk normal distributions, is $3.61. The plain vanilla price is $5.08. Now, a little bit of insight on why it's cheaper is the volatility of an average of 3 numbers is going to be less than this single value at the end. So that's why it's a little bit cheaper to buy these arithmetic Asian options than it is to buy a option that depends on one number at the end. Last thing I'll talk about is why would anyone want an option that does this? Well, maybe you're a brokerage firm that's trying to hedge your revenues or your expenses, and your revenues to depend on what happens to the stock market each month. So you don't want an option that simply pays you based on what happens to the stock price at the end of the year or the quarter. You want ones that pay you each month if the stock price winds up being high or low. So if you're a company that has exposure to how the stock price goes over the entire life of the option versus just what it ends with, I might want an arithmetic average option and not a simple European strike in this case. So in this topic, we just talked about how to value an exotic option using our Monte Carlo model and also using that risk-neutral simulation formula that we talked about in topic 2 and talked about in topic 3.